So let's suppose we've got a very simple idea. We just have two buttons, and when we press both the buttons, we want the light to be on. Maybe this, I know this is kind of a morbid example, but it reminds me of uh, the case for like the nuclear missiles where you see they have the two keys and both the keys have to be engaged before the missile launches. So that's kind of what this is in my head. But it's a lot simpler than that, really. Anyway, so we've got two buttons that need to be pressed, and once they are pressed, we turn on an LED. And of course, there are some ways that we could wire the buttons to do this, but we want to use digital logic. Um, so we have to ask ourselves, what can we do, or what kind of gate has an output of 1 when both of the inputs are 1? So give you a second to think about that. And yeah, so it's an AND gate. So if we, oops, I always forget, can't drag. So we want a 2 input AND gate. So here I'm just setting the inputs to 2. We want a 2 input AND gate, and we're gonna wire our inputs here. So button 1 is connected here, and button 2 is connected here. And one of the things that I should note is uh, I could hook button 1 here into this input and button 2 here, and it would still work the same, meaning that it's commutative, right? The AND gate function doesn't care where your operators are at, or the operator doesn't care where your variables are coming in. They can be in any order. And then we're just going to take our output and hook it to the LED. And so let's kind of simulate this and see what happens. So right now, both the buttons are at 0, meaning that they're not being pressed. And if I press one of them, you can see the signal lights up. But the AND gate is waiting for both of the inputs to be 1 before its output is a 1. So then I press this guy, and the LED turns on. I turn this off, it goes off. The moment this signal changes, the output also changes. So there's a very simple example of what you can do with digital logic.